So coming to our lectures, we see that the, the columns of the R1 to 0 matrix are the unit vectors. The unit vector I1, that is the unit vector of the frame 1, I of the frame 1, expressed in terms of the components of frame 0. The second column is the unit vector J of the frame 1, expressed in terms of the components in frame 0. And same for the unit vector K1. We could understand that because here we are taking I1 and we are taking the dot product with the respective directions. And you can see for yourself that the magnitude of this, you see, these are all going to be direction cosines. And the magnitude of this is going to be the magnitude of the unit vector I1. And the magnitude of the unit vector I1 is actually 1. The same applies for the magnitude of the unit vector J1 and also for the magnitude of the unit vector K1. So the magnitude of these columns, each of these columns is 1. These columns are also mutually perpendicular to each other. You see, I1 is perpendicular to J1, J1 is perpendicular to K1, K1 is perpendicular to I1. So these columns are mutually perpendicular or orthogonal to each other. So this is also an orthogonal matrix. Orthogonal matrix. You can see that there are two restrictions on this. One is that the columns are orthogonal, and secondly, that the magnitude of each of these columns is restricted to 1. So when we restrict the magnitude to 1, it's like normalizing a column, normalizing the value. Okay. And that is why we call this matrix as an orthonormal matrix. I hope this point is clear to you. The columns have magnitude 1 and they are mutually perpendicular to each other. So that's the reason why it's called an orthonormal matrix. Normalized with respect to a normalized magnitude is normalized to 1. Let us proceed further. Let us write. Yes, we also saw that for this special matrix, we could write R inverse of this matrix as its transpose. And this doesn't happen in general. This happens specifically for this matrix only. So that is the property of orthonormal matrices. So this is the orthonormal property of R, that R inverse is equal to R transpose. Okay, and we have seen that in our last lecture. We saw that we had seen that the columns here have become rows here. So I1 has been resolved in terms of components of frame 0 here and shown here as a row. And if you see the columns over here, you will see that you have the vector I0 being expressed in terms of the directions of the frame 1. So it is the unit vectors of frame 0 being expressed in terms of the frame 1. So this matrix is just the transpose of the matrix we had earlier, that is R10. And we know that this is also the inverse, and so the inverse is actually equal to the transpose in this case. So let us have a look at, let's go to the next R matrix. R1 to 0. It's a square matrix. So usually matrices that are not column or row vectors, we will represent them using brackets like this, square brackets. And here it is unit vector of frame 1 being expressed in terms of the components of frame 0. Each one is a column. So this is the first column of R. The second column of R is here. And the third column of R is here. We could also write this matrix as the first row of this matrix is I of 0 expressed in 1, transpose of that. Unit vectors of the frame, unit vector I of the frame 0 expressed in terms of frame 1. This is J of the frame 0 expressed in terms of 1. But you see that the column has now become a row. And here we have K. So the same matrix can be written in these two representations. Okay. Now, when you take a product of this, let's say when you take R1 to 0, transpose operating on R1 to 0. We know that the transpose is its inverse. So actually this should be equal to a unit matrix. Let us write this unit matrix as I matrix. But this I matrix is a 3 by 3 I matrix. Okay. So 3 by 3. And we could also write this. You can see it for yourself. You can also write this as R1 to 0 R1 to 0 transpose. I suppose you have done the properties of orthonormal matrices, etc. But now you get to see for yourself its application in the specification of the orientation of frames relative to each other. So when you multiply R1 to 0 transpose with R1 to 0, you get the unit matrix. Okay. I hope it's clear to you, or do you want me to elaborate on this? Can I have your feedback, please?
Yes, sir. Sir, this is matrix property. A transpose equal to I, A transpose A equal to I.
Yeah, it is not. It is not in general. It doesn't happen for all matrices. See, normally usually what happens is A inverse A is equal to I. Okay.
Yes, sir.
It is not that A transpose A is equal to I in general. Got it?
Yes, sir.
A inverse A is equal to I. A inverse is equal to I. But R is a very special matrix. Because of its orthonormal property, its inverse is its transpose. Are you clear about it? Or do you want me to elaborate? It
Yes,
does
sir.
not
Clear.
happen for all square matrices. It happens specifically because of the properties of the R matrix. Is it clear?
Yes, sir.
Yeah. In general, you will never find that the transpose of a square matrix is its inverse. It doesn't happen in general. It is for the R matrix, which is a special matrix, and that's the property which I explained to you in terms of the column vectors and the column and the row vectors of the R matrix. Okay. If you want, I can also expand this and show you how you get one, how you get the unit matrix. Now, we saw that there is a restriction on the magnitudes. Each of these columns has a magnitude of 1. Now, how do you specify that? We can say that the magnitude of this column is equal to 1. In uh, terms of magnitude, we can say that the length of this vector is equal to 1. And how do we specify the length of this vector? We can say that I, this vector, this unit vector, its length is equal to 1. That means its norm is equal to 1. In general, for those of you who are not familiar or who need a refresher, it's just that you can, if you have a matrix in general, if you have a vector, let's say you have a vector A, and let us say that A has elements A1, A2, and so on. And you have a number of elements like this, say you have n elements, an. It's a column vector. Okay. So you can say that the magnitude of or the length of this vector is given by, you have done this before, it is just a1 into a1, that is a1 square plus a2 square plus a3 square and so on up to an square, and you take the square root of this. We also call this the Euclidean norm. Okay. So you have the length of this. We can also write this in terms of, a dot product. What is this actually? It is summation of ai square and square root of that. Okay. I equal to 1 to n. So you are determining this. We can also write this in terms of matrices as A transpose A. Okay. You see, A is a n by 1 matrix. A transpose is a 1 by n matrix. Okay. These are arrays. This is a column array. This is a row array. Okay. So when you take the product of these, when you do A transpose A, what you are doing essentially is you are taking a dot product of A with itself, and this is equal to AI square summation. You are just taking the square root of this. Is it clear? So we can write the norm of A like this. I hope it's clear to all of you.
Yes,
So
sir.
Yes, sir.
what we have shown here is the norm of this vector is actually the length of this vector. So you're taking the components, you're squaring them, and then you're adding the squares, and then you're taking the square root. And you find that this length is actually equal to 1 because it's a unit vector. Its length is actually equal to 1. Okay. So this is how we represent. So for the columns of the R matrix, this is the second column of the R matrix. This norm of this also is equal to 1 and K 1. So we'll do a few simple cases and things should become clearer to you. So these three magnitudes. So we have got three conditions now. The columns are equal to 1 in length. Okay. So these are our first three restrictions on the elements of the A matrix. There are 9 elements, but these are the restrictions. Now, what is the next restriction on this? It's an orthonormal matrix. Normal part we have said. Now comes the ortho part. They are mutually perpendicular to each other. How do you specify that two vectors are mutually perpendicular to each other? You take their dot product, right? And the dot product of these two vectors mutually will, if they are perpendicular, what will be the dot
Zero.
product?
0,
Zero.
0.
It will be 0, right? So the dot product of mutually perpendicular vectors will be 0. That means if we take the vector I and I take its dot product. Now, how do I take the dot product? How do I write it in matrix form? I'm going to write it like this: I transpose J. Okay. This is going to be equal to 0. Now, suppose we have another vector here, just like A. Suppose we also have B, and say B is also equal to B1, B2, and so on up to Bn. Okay. What will A transpose be equal to? See, A is here. So we will write it. So we will write A transpose as equal to A1, A2. This was a column. Now it will be a row. AN. Okay. This is our A transpose. This is the transpose of this A transpose. And what about B? We'll write it as it is here. B1, B2, Bn. Okay. When you take the dot product of this, it is equivalent to multiplying these two matrices in this order. Okay, these two arrays. What do you get? You get here.
A1 B1 plus A2 B2 plus
Yeah, precisely. So here you get A1 into B1. I'm not going to put this dot in between because it has a specific meaning. Of course, these are components, they are scalars, plus A2, B2, this into this plus this into this plus and this into this. So A2, B2 plus and so on up to AN, BN. Okay. So we also write this as A transpose B. Okay. So instead of writing it as a dot product as we do using vectors I, J, K, we'll write it as I transpose J. I hope the meaning of I transpose J is now clear to you. It's a dot product. You are taking the dot product of this vector with this product, with this vector. A transpose B, I transpose J. Okay. And it's a scalar. And you can see that it is also equal to, you could have also taken it as B transpose A because it's a scalar. Okay, you can also take this as B transpose A. It's the same thing. Okay, the product is just summation A I B I being summed from 1. So this is the meaning of this. So you can write this as A transpose B or B transpose A because one is the transpose of the other, but it's a scalar. And because it's a scalar, the transpose of a scalar is also the same thing. Okay, so this is I transpose J is equal to J transpose I is equal to 0. And so we can also write the other elements. We can also write the next condition, that is J transpose. So J1, okay, transpose K1. These two unit vectors, these are also going to be equal to 0. We could also write it as K transpose J. Okay. And in the same way, you can also write K transpose I. This is also going to be equal to 0. You can also write this as I transpose K. Okay. So now you have got 6 restrictions on the elements of the R matrix. What are those? First one, second one, third one, fourth one, fifth one, sixth one. So you have got 6 restrictions on these 9 elements. Naturally, it means that if you have 9 elements and 6 restrictions on these relations, it means that you can have 3 independent elements which can actually do the same job. Okay. So actually to specify an R matrix, we don't really require 9 elements, but just 3 elements are sufficient. Three quantities are sufficient. Is it okay? So So, but these may not be unique. These three quantities may not be unique, and that's what we will see later on. They'll produce the same result, but we could have different quantities producing the same result. So that's the reason why uh, we could have different ways of specification of R. We'll do this in our subsequent lectures. But for now, I hope the properties of the R matrix, the constraints on the elements of the R matrix, these are clear to you. Okay. So here we have 9 elements of the R matrix, and we have 6 constraints, 3 related to length and 3 related to their mutual orthogonality. So 6 constraints. And so R matrix, the elements, R matrix actually can therefore be specified in terms of just 3 independent, we may call them variables, or we may call them values or numbers. Okay. Now let us proceed further. Let's take an example. We have talked of the R matrix. Now let us try to do some standard examples which we already are familiar with, but which we take for granted. So this is your x-axis. This is the y-axis. Let's say, and we have the unit vector corresponding to the x-axis. Let's say this magnitude is 1 because it's a unit circle. So this vector is I0, and this is J0. Likewise, we have here the unit vector corresponding I1, and so we have the frame 1 here. The frame is indicated like this. It's frame 1. And this vector here is I1. And this vector here is J1. Magnitude of all these unit vectors is 1. We also have to indicate this. This is the frame 0, which is in black. We'll show it. Okay. So the K vectors of both the frames, they're coming out of the paper. It's you're using the right hand rule. So you're turning from I towards J, and your thumb is pointing towards the positive direction K when you're using your right hand. So this is K0 as well as K1. K1 also is here itself. Let's say that the angle which is turned from the angle between these two axes is this angle is we can show it here itself. This angle is theta. This angle here from here to here, this angle is theta. Starting from here to here. So if we try to resolve this, if we try to write the R matrix R120, what will this look like? We can take the components from our earlier slides and let's write down the components. Now what is here we have the vector I1 and we have to resolve it in terms of the directions of the frame 0. So if we see the components of I1, we will be able to write it like this. Okay, so we have the components over here. We have this component. This component is I1 dot I naught. I1 dot I naught. Okay. This is I1 dot J naught. What is that? So here I1 dot J naught is here, this component. I1 dot J naught. And I1 dot K naught. You see I1 is here and K naught is perpendicular to it. So I1 dot K naught is actually equal to 0. Okay. So here we are having, now what is I1 dot I naught in terms of theta? You see magnitude of this is 1, magnitude of this is 1 and the dot product of this is what? Cos of the angle between this. So this is actually equal to cos of theta. Do you agree?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
I1 dot J naught. What is this? It is corresponding to this,
0.
and that is equal to opposite side of this right angle triangle. Okay, so this will correspond to sine of theta. Okay, so this is equal to sine of theta. Sine of theta. This is corresponding to cos of theta, this one. Okay, and the third one is equal to 0 because I1 dot K naught is actually equal to 0. So we have the first column as like this. So first one will be cos theta, correct? Cos theta. This will be sine theta, and this will be 0. Thank you very much. The second one is J1. You see, J1 is over here, and that is being resolved along the two directions. So again, we have to resolve it. So we take J1 and we resolve it along the directions of frame 0. Okay. This angle that we have here, this angle is theta. This is theta. And the magnitude of this is 1. The radius of the circle is 1. So you have first thing, that is J1 dot I naught. You see, J1 and I naught is here. So you are taking the dot product of these two. That means it is the projection of J1 along I naught, and you can see it is this one. It is pointing in the negative direction. That means it is minus. What is the magnitude of this? It's the opposite side here. That is sine of theta. So this corresponds to minus sine of theta. Then we have J1 dot J naught. So J1 dot J naught. So it is actually the projection over here, this one. Okay, so this is J1 dot J naught. And this is how much? It is the adjacent side corresponding to 1. So 1 into cos of theta. So this is actually just equal to cos of. Okay. So this is just cos of. And the third one is J1 dot K naught. K naught is perpendicular. So naturally this will be 0. What about the third column? K1. You see, K1 is coming out of the board. So it's perpendicular to I naught, it is perpendicular to J naught. So naturally these two elements will be 0. But K1 dot K naught, you see, both are in the same direction. The magnitude of both is 1. So 1 into cos of 0.
1.
That is
1.
So you can see this is actually the R matrix that is corresponding to, it is specifying the orientation of the frame 1 with respect to the frame 0 for this simple case. Here what we have done is we have rotated. So we have got here the x1 axis here, and we have got y1 axis here. Okay, so we have rotated. In fact, we have got this frame x1 y1 as oriented with respect to frame x0 y0 by an angle of theta, and this is how we are able to specify the orientation of the frame 1 with respect to frame 0.